Kostas, and together with Leila, we have been working for a long amount of time in the field of hardware security. So for the last 6 or 7 years, we have been working together in the Netherlands on this field. So the goal of this webinar today is for me to give you a quick introduction into physical attacks. What are physical attacks? What can they do? Why should we worry? Or can they do any harm? Or how should we protect against them? And of course, I also want you to give you some information on the course that we are having in hardwear.io. And we have been, we keep on doing this for the last couple of years. It's called Embedded Physical Attacks 101. So let me get right onto it. Right. There are 3 main questions that I would like to, let's say, discuss with you and during this webinar. The very first one is how did we get here? How did we get to the point where physical security and physical attacks are important in the life cycle of a device? And interestingly enough, this relates a lot to the history of cryptography from the 70s up until almost today. And I will a quick trip down the memory lane, a very quick trip down the memory lane so that you can take a look and see how did we end up with this line of attack and how much harm they can do. The second question that I will try to answer is what are the physical attacks? And we will see that there are 2 main, let's say, types of such attacks. One of them is side channel attacks, and the second one is fault injection attacks, and we will talk briefly about both. And finally, the last question that over in this course, what are the prerequisites, and of course, what do you need to know and what you should expect. All right, so let's get going with the very first question is how did we get to the point that physical security is important? Okay, so I will start a bit with, let's say, quite some time ago in the 70s and 80s. Well, that was a time of rock and roll, but also it marked the birth of modern cryptography. It's quite interesting because many of the early cryptographic designs, they surfaced during that era. DES, RSA, and many other structures were proposed at that time in 75 and 77. And of course, that was the beginning of our field, the beginning of security in cryptography in many ways, and people started analyzing those mathematical structures. At that time, it was pure. Even more interesting, that was the era where things became increasingly more open. So what used to be, let's say, the field of the military or secret services, it kind of moved more into the public sphere of influence. So therefore, we moved from closed approaches into an open community, an open academic community that was in favor of cryptanalysis. So at that time, the workflow of a cryptographer or a security analyst was quite, well, no, I'm not going to say it was easy, but it was straightforward. You had to construct a cipher, and you had to make sure that it resists mathematical attacks. And of course, you had to convince other people about it. And the RSA was, let's say, solidly based in a mathematical problem, but DES in many cases did not make the cut. All right, the last part, and probably the more interesting one, is where do we use cipher? What are you trying to do with it? And back in old times, there was just a mainframe that it would rest there for every user. So at that time, the goal was, let's build some good cryptography. The goal was not so much, let's implement it efficiently or let's implement it securely. We focused more on the theory as a community. Now, taking the next step into this discussion, cryptography in the 90s and 2000, it moved in a different direction, kind of like music moved to hip-hop music. So in this era, which is closer to my age, we have the widespread let's say, effects of personal computing, which were becoming more and more evident. The internet became even more popular, broadband connections, and so on and so forth. And at this time, security evolved with it. So suddenly, everyone had his own computer, everything was connected on the network. And of course, every computer was vulnerable at this time. you had to use strong encryption to protect everyone. So this was the consensus that people reached in the 90s, that every device should be well adequately protected with something that is built in and effectively encrypts data within it. All this effort piled up and built the advanced encryption standard in 1998. What is quite interesting in this design is that the first time people started considering not only the crypto as a mathematical, as a, an abstract theoretical concept, but as something that you put in a device and used to be efficiently implemented. That was the first time that this became very evident. Of course, so AES should be both secure and efficient. And the workflow of the cryptographer or the security guy, if you like, it shifted a bit. Of course, you need the cipher, it must resist mathematical attacks. But for the first time, you need to make sure it's fast and that you put it on your personal computer or any other computer around, or a laptop. So that was, let's say, the 90s and the 2000s in crypto. We had more solid foundations and we moved more into the hardware side of things, more closer to the physical aspects, if you will. Finally, we reached the modern days. So what about cryptography in 2010 and 2020? So then cryptography and the whole computing paradigm shifted to, let's say, a more pop feeling, I would say. So it used to be that everyone had his own computer, but now every little device that everyone would access constantly was suddenly connected to the internet and it needed protection. So not only your computer, but now your smartphone, every little sensor in the Internet of Things. So with a much more intense popular feeling, all those devices, all those embedded devices were always online and they were endless, or so many of those. And as this shifted, we all started using smartphones, smart cards, dongles, RFID transport cards that we used to go into the bus every day. And every one of them had critical data. And more importantly, everyone was open to attacks. You could try to attack, you could try to hack your card. You were the user and the attacker at this time. It was actually quite interesting. The workflow changed a lot. You still were building cryptography. It should be resistant. It should be very efficient. But now it's going to be distributed to everyone. It's going to be on every imaginable device. And it's going to go to everyone that uses, for instance, the train system or an ATM machine. Cryptography, like computing, actually, this was in my mindset at least, it was the breaking point. It was the point where hands-on device was very easy and everyone could try hardware hacking. So what used to be, let's say, a sphere of some very specialized people became much more open due to the big availability of devices. And many people gave a strong effort to try to hack many devices. And more interestingly, many products were found insecure when put under scrutiny. So just to mention a few examples that are quite notable in the community, the Xbox had serious hardware security issues. I do recall people modifying PlayStation chips so that they can play cracked games. Pay TV was affected a lot because many people managed to do physical hacks on pay TV and essentially watch it for free. And of course, this spilled over the smart world as well. So on the right one hand here, it's quite important because it is the Dutch transport card, which was hacked quite some time ago. And of course, you can write for free if you use it carefully now. So that's where we are. Everything became really available and people trying to find hacks and issues in it. Now, the next step is, okay, we've seen that these attacks exist. They can target real world devices. My next point now is what exactly do they do? And what exactly can you expect from it in the scientific way? So as I said, we have two lines of attack. One of them is side channel attacks, and the second one is fault injection attacks. So I feel the best way to describe side channel attacks is with a quick example. So I want you to take a look at this little piece of code. The input of this code is a 4-digit PIN code, and the output is a yes or no. Is the PIN verified or is the PIN rejected? So you build a process, and perhaps you're not a very good programmer, for instance, and you build a very strange process, which is a bit like that. It's a bunch of 1, 2, 3, 4 nested loops. And let's try to see what it does. So you have an outer check. If the pin is 0, is equal to 5. If pin 1 is equal to 9. If the second digit is 0. If the third digit is 2. Then if all the checks are met, you are in the final part of the nested loop and the pin is okay. Otherwise, the pin is 0, which means not okay. And what is interesting about this example is that this little piece of code, although strange, it's functionally correct. It does the pin check, it gets the job done. However, it may be vulnerable in ways that we did not predict in the past. So if you become a little more curious, you may try to, try pins yourself. So what would be the execution time if you try like a pin code 0, 1, 2, 3? Then you will end up here, and in the very first if condition, you will fail. So probably that will run for some time, but not too long. Now, what happens if you get the first digit correct? Then the is 5, you will fail in the second loop. So it will take a bit more. And what if you get more digits right? And in the end, you're going to figure out that as you get closer to the correct pin, which is 5902, your execution time becomes higher and higher. So you have a perfectly correct piece of code in the sense that it does the job, yet there is what we call a side channel, some accidental information, like time, which reveals information about the secret pin or the secret key, possibly. So just to define it a little bit, a side channel attack will observe data from the physical device, and then it will use it to bypass security. So you may have a cryptographic device that does AES or DES or RSA in a perfectly sound way, in the sense that AES is mathematically secure. However, once you put it on the device, so you move away from the 70s and the 80s and you go into the 90s and modern day, and you have things inside the device that rests on the palm of your hand, then you can start observing the data and you can start using this data, this accidental data, to bypass your security. So finally, the workflow needs to change. And this reflects upon the changes in the crypto community. Start with cipher, it has to be a good cipher, but you also need to be sure that it will resist such accidental leakages. It will resist side channel attacks, as we know. And of course, once you do that, then you can have a certain security guarantees that even if you hand out those devices to everyone, it's still quite hard to hack into them and get the key or clone them or do similar things. First, we discussed about execution time. There are even more popular side channel techniques that involve power consumption, electromagnetic emission of a device. So typically what I like to show is a simple device like that. So here you can see a microchip, and here you see a small antenna that rests on top of it. And while AES is being executed, the power consumption is being measured, and you can see it in signals here. So in this context, it's actually quite interesting to see that even small variations and statistics can help you find the secret key just by observing those fluctuations over time. And we do have assignments of that during our course. All right. Let's move now to the second part, the fault injection attack part. And once again, like in side channels, let me give you yet another example. So let's say that you want to, do an AES encryption for certain plain text over here. And what you have to do is to go for 10 rounds and do the pieces of the AES software. Add round key, S books, shift rows, mix columns. And finally, you're able to produce the ciphertext. Now, what if, this is a big if, but what if you can somehow tamper a little bit with the voltage, just enough at the right time, hopefully, so that this variable, instead of going from 1 until 10, gets stuck at 0. What if this would happen? Then essentially your for loop is done, and there is absolutely no encryption at all. Essentially, you're able to bypass the AES encryption. So, fault injection attack is an attack that alters the data in the physical device and uses this data to bypass security. It's more active compared to side channel, far more active. And of course, now your workflow changes. And before you hand out something to the public, you need to have a good cipher, secure in the mathematical sense, but very importantly, secure against side channels and fault attacks as well. And same like in side channels, several fault injection techniques. There's magnetic glitching, there's laser injection. So some people have complex setups and they put one chip underneath the laser and they're able to shoot at the right spot and make a variable 0, and bypass the encryption, or something in a similar world. All right. Now I've reached the final question of this webinar, and this is what we cover in the course in hardwear.io. And briefly remind you standard encryption algorithms like AES and RSA. We will need concepts from cryptography. However, if you are not fully familiar with those algorithms, there's no need to implement them. We assume that they're already in place inside the embedded devices, and we will try to hack them. However, while hacking them, it's quite good to remember their basic structure. So if you feel like attending the course, do freshen them up in Wikipedia, and we will also be offering an introductory discussion on how this cipher works in case you need to remember. The second thing is side channel in this course, and there are two things. So first thing first, we cover quite a lot of data analysis. So we give you side channel measurements, specifically power measurements and electromagnetic emission measurements. And then we will teach you, we will not give you an automated tool that does a side channel attack. We will teach you how to code and of course, we will use this code and we'll analyze those side channel measurements in order to extract the crypto key. So for every assignment that we do, okay, there is some reward in the end. Like if you manage to code the attack correctly, then you will be able to get out the secret key of the device. And of course, we aim for this process to be as much as interactive as possible, in the sense that we will be discussing and helping you with coding this data analysis attacks. We cover most side channel techniques, so like simple power analysis, differential power analysis, correlation power analysis, and the slightly more sophisticated template attack. Rely on some concepts from statistics, quite simple. And we will be throughout the course, we will be teaching and reminding those concepts to everyone. All right, there goes data analysis. Now, with respect to data capturing is a more, let's say, tricky process, but we have several chip whisperer devices where you can easily capture data, and we will hand over those devices so that you also get a feeling not only through this coding, we will be using MATLAB or Octave, or Python with NumPy. So if you feel like, we always run a quick tutorial in the beginning where I remind you how for loops are in those languages. But if you feel like, you can definitely take a look at basic coding techniques with those things, so just that you get faster. In general, we don't assume any prior knowledge, just that you can code simple things like for loops, if conditions, and use certain built-in functions that we will be discussing together. All right. Fault injection in this course. With fault injection and the chip whisperer setup, once again, we will produce some voltage glitching effects, and we will be using them to recover the secret key of RSA using one of the standard attacks. And this involves some Python coding. So yes, do take a look, and we will be discussing this in detail. All right. So, of course, here you the course description and our CVs. They're also available on the website. That's Leila and me. We have been running this training for the last years together. And if there are any questions, something that isn't clear to you or something of the like, yeah, feel free to contact us and drop us an email at any of those addresses. Thank you very much for attending, and I will be very happy to receive any questions.